As the technology of man in space was developing, it became more and more apparent that our knowledge of the moon's surface as a possible landing site was not sufficient. To land man safely on the moon and get him safely off again, we had to know whether we could set up a precise enough trajectory to reach the moon. Could we design and build a spacecraft to land gently on the moon? Among all those lunar craters, could we find a place clear and level enough for a safe landing site? To make it possible for a man to land in the Apollo zone on the moon, better pictures were needed than those taken through Earth's best telescopes. In fact, better pictures might do more than find a landing site for Apollo. Scientists hoped they might resolve questions unanswered in the 300 years since Copernicus prompted Galileo to study the moon.
Surveyor was conceived to answer such vital questions as well as to survey possible target sites for the forthcoming Apollo manned landings. Hughes Aircraft Corporation was selected to develop the spacecraft under the overall project management of the Jet Propulsion Laboratory, California Institute of Technology. Because of its highly demanding mission, new design, engineering, and construction techniques were required for Surveyor. The launch vehicle system is a new, more powerful booster combination, the Atlas-Centaur.
AC-4's primary test requirement is to inject the Centaur upper stage into a circular orbit on a one-burn, direct ascent trajectory. The vehicle has a Surveyor mass model, a spacecraft mounting adapter, and a newly designed coast phase ullage engine.
The new ullage engine installed on the AC-4 aft bulkhead is designed to prevent the propellants from floating free in the tanks during the coast phase period. The engine is a modified attitude control cluster uprated to 4 pounds total thrust. The 2 hydrogen peroxide thrusters will fire continuously during coast phase, maintaining the propellants in the aft end of the tanks ready for the second burn.
On previous flights, Centaur flew a trajectory plan to insert the vehicle into orbit at about 300 nautical miles. For AC-4, orbital insertion is planned at about 90 nautical miles. As a result, Atlas-Centaur remains in the Earth's atmosphere longer and experiences increased aerodynamic loads and heating as it pushes its way through the denser regions. The most important primary objectives of the AC-4 flight test are to verify the performance and structural soundness of the nose fairing and insulation panel systems, demonstrate overall vehicle structural integrity, and demonstrate the guidance system accuracy, performance, and system integrity. For AC-4, the all-inertial guidance system will operate in a closed-loop capacity for the first time. It will assume command at booster staging and will direct Atlas-Centaur, controlling flight events aboard both vehicles. Before Centaur's guidance system could be considered flight-ready, it had to pass a series of design proof tests at Astronautics.
Since June, we subjected the guidance set to 12 different proof tests. 9 of them have been an exposure to a severe environment. The first 6 had to be completed before AC-4 could fly. These included performance, temperature, shock, acceleration, and vibration checks. The 6 design proof tests constraining the flight were completed in September.
AC-4 is also the first Centaur to fly a mass model of the Surveyor spacecraft. The 2,100-pound model is a relatively simple structure and represents the Surveyor only in weight and center of gravity location. It will not separate from Centaur during flight. With most of the ground tests complete and only a few constraints remaining, the Surveyor model, Atlas 146D, and Centaur 4C were airlifted to the Eastern Test Range.
After systems checkout, launch crews mated the vehicles on 20 August. Tests were progressing with launch scheduled for October. In early September, Hurricane Dora threatened the Cape, and as a precautionary measure, test range crews removed the vehicles to a safe area. AC-4 was down for 8 days. In October, launch was again delayed when, during an integrated tanking test, the AC-4 liquid oxygen tank overpressurized. A faulty liquid level sensing tube gave a false reading and continued pouring liquid oxygen into the already full tank, developing overpressurization. X-ray leak checks did not reveal any defects or ruptures in the tank or bulkhead. With confidence in the tank's integrity, crews recycled checkout procedures and began guidance launch alignment, the last constraint to the AC-4 flight. AC-4 is the first Centaur to employ optical alignment to orient the guidance platform into the selected launch azimuth. A light beam leaves the optical equipment shelter and enters the nose fairing through an optical window. It then strikes a reflective prism on the inner gimbal of the guidance platform. An operator remotely positions the inner gimbal until the prism reflects the beam back to an alignment theodolite. The platform then locks into a stable position to provide inertial reference during flight. Optical alignment is about 5 times more accurate than gyro compassing used on previous flights. The theodolite holds the guidance platform captive until 15 seconds before launch. December 11, 9:25 a.m.
All recorders are fired. 14 seconds. Initiating engine start. On its 8. Please start. Ignition. Release. Looks good. Right in the broken. We have a little water on the pad. It's good.
I'm Andrew Kalatinsky, Assistant Program Director of Centaur for Engineering here at General Dynamics Astronautics. This flight was the most heavily instrumented to date. Of the 650 telemetered measurements aboard Atlas and Centaur, 99% yielded usable data. This was the 26th consecutive successful flight of an Atlas booster. The operation of all Atlas systems were nominal throughout booster phase. This was the first Atlas Centaur flight with Centaur all-inertial guidance in flight command.
Rico. Booster.
At booster cutoff, the guidance system controlled both Atlas and Centaur for the remainder of the flight. The insulation panels and nose fairing jettisoned smoothly at the prescribed times. Atlas and Centaur separation and Centaur main engine ignition was equally smooth. At T plus 573 seconds, Centaur main engines cut off as predicted, and the vehicle then began a controlled coast in a near-perfect circular Earth orbit. At this moment in time, we had achieved all the primary flight test objectives. We also had again demonstrated a single-burn, direct ascent type mission that will satisfy the presently planned operational flights scheduled to place Surveyor on the Moon. However, concurrent with our Surveyor flight test program, we're looking towards the future when it will be desirable to have a two-burn capability. That is, Centaur will coast in a parking orbit for a time following the first burn. The engines will ignite again and thrust the payload into a lunar or planetary intercept trajectory. The two-burn approach will give us a considerably broader launch window. However, the coast phase imposes a number of technological unknowns. In order to acquire advanced experimental data on the behavior of cryogenic propellants in the zero-G coast period, we added a coast experiment and a planned engine restart as secondary flight objectives for AC-4. At the beginning of the coast period, the propellants float free in the vehicle's tanks. Two small ullage rockets mounted on the aft end of the vehicle, capable of 4 pounds thrust, were commanded to start at main engine cutoff. The engines were designed to apply forward thrust to settle the propellant in the aft end of the tanks, ready for the second burn. The AC-4 flight result indicates that the 4-pound thrust is not sufficient. The thrust level selected was based on the interpretation of tests with small-scale tanks in a short-duration zero-G environment. These small-scale tests did not give us accurate data reflecting propellant behavior in a full-scale tank in a true space environment. The AC-4 vehicle maintained attitude during the coast period until the hydrogen tank vented 267 seconds after main engine cutoff. There is evidence that the propellants had not settled completely. Liquid hydrogen exited through the vent valve and in the vacuum of space expanded with a force much greater than if the gas alone had been venting. Gas impingement on the forward end of the tank then pushed the vehicle in yaw with a force greater than the attitude control rockets could handle. As a result, the vehicle began to tumble, further aggravating the problem of keeping the liquid hydrogen at its pump inlet. All pre-start commands were initiated, indicating that all systems were functioning normally, but engine start was not achieved due to propellant starvation. As a result of the AC-4 experiment, we acquired vital information relative to propellant behavior. This is not only valuable to future Centaur two-burn designs, but to all space programs that are using cryogenic liquids in a zero-G space environment. AC-5 will fly a lightweight slosh baffle, an advanced propellant utilization system, and a Surveyor dynamic model.
The first of the advanced propellant utilization systems for Centaur was installed in AC-5 on 10 April. The system is designed to achieve payload gains by controlling the mixture ratio of liquid oxygen and liquid hydrogen so that no more than 150 pounds of one propellant remains at the depletion of the other.
The main objectives of the AC-5 and 6 flights will be to place a dynamic model of Surveyor into a simulated lunar transfer trajectory. The Surveyor model will separate from Centaur and fly on a course in the direction of an assumed or paper moon.
The dynamic model consists of 3 main assemblies: space frame, a retromotor simulator, and an S-band transponder. The Surveyor model is non-functional, except for telemetry and tracking equipment and instruments that measure in-flight environment during the boost phase of launch. Shortly after the Surveyor model separates, Centaur will perform an in-flight turnaround and retro maneuver. Residual propellants will discharge unignited through the main engines, slowing Centaur down to increase the distance between it and the payload. On operational flights, this maneuver will prevent Surveyor's guidance from locking onto the tank as a navigational reference. March 2nd, flight day for the 5th experimental Atlas-Centaur AC-5. Its mission objectives: to verify flight results to date and demonstrate 4 new systems, including the release mechanism for payload separation. This was to be the first time a dynamic model of Surveyor would separate from Centaur and begin its flight to a hypothetical point in space, a paper moon target. Countdown proceeded smoothly to T-minus 5 minutes. Then the count held 40 minutes to demonstrate Atlas-Centaur's ability to stand fully fueled for a pre-planned length of time. No system degradation due to cryogenic effects was noted during the hold. After an almost perfect countdown, AC-5 launched on time at 8:25:04 Eastern Standard Time. At the time of the flight, the Atlas launch vehicle had set a record of 28 consecutive successful flights without a mishap. Analysis of motion picture films did not reveal abnormalities in any systems until flameout of the thrust chambers. All that was known was that 2 seconds after liftoff, Atlas booster engine shut down and the vehicle fell back into the launcher where explosion and fire destroyed it. Test data showed that all engine sequencing and thrust buildup was normal until loss of fuel at the B1 and B2 fuel pump inlets. Examination of actual engine system hardware indicated that thrust loss was caused by fuel starvation. The most probable cause was closing of the fuel pre-valve, which blocked fuel flow to the booster engines. The pre-valve is located at the outlet of the RP1 tank and is used during pre-flight ground operations to keep fuel out of the engines and to maintain tank pressure during maintenance or storage. It also serves as an emergency fuel shutoff during engine testing. Detailed analysis of recovered hardware revealed that the pre-valve was closed at the time of the pad explosion, indicating that it had not locked fully open before flight. A pneumatic actuator operates the pre-valve. It is designed to lock the pre-valve open by means of an internal ball detent mechanical lock. Examination of the actuator mechanism showed no evidence of mechanical flaws to prevent it from stroking fully open and locking. However, bench tests revealed that several complications could be induced which would permit the pre-valve to partially open to a semi-locked position. Even though the valve is not locked fully open, a full open indication could be received at the control console. Flow tests at the Point Loma test site showed that fuel flowing through the semi-locked valve initiates enough force to close the butterfly flap, shutting off flow to the engines. Immediate corrective action involved installation of a mechanical locking device on both the booster and sustainer fuel pre-valves.
The launch stand and umbilical towers were badly burned, but pad damage proved less severe than it had first appeared. The launcher, wiring, ducting, and the transfer room suffered the most extensive damage. The task of repair involved cleaning and replacement of burned-out parts, followed by validation of systems. The biggest problem was to get lots of parts and cables in a hurry. Fortunately, many of the major items, for example the launcher, were available from the disaster pool maintained by the Air Force. The steel beams in the umbilical and launch towers did not sustain structural damage and only needed cleaning and painting. Most of the rehabilitation task had been completed by the end of June. At that time, validation of ground support equipment and systems was underway. The complex will be ready for launch operations by late summer of 1965.
The AC-6 R&D configuration represents the operational design for one-burn missions. A number of major changes were incorporated in the AC-6 flight vehicle tank and structures. Centaur designers achieved extensive weight reductions on the tank and in the interstage adapter. They reduced skin gauges, chem-milled the forward bulkhead, lightened the thrust barrel, eliminated the wetting ring, and moved the intermediate bulkhead back 4 inches. Moving the bulkhead aft reduced the ullage space in a liquid oxygen tank, eliminating the need for a slosh baffle. At the same time, it increased the fuel capacity in the liquid hydrogen tank by 26 cubic feet.
The attitude control clusters moved from the attaching ring to the aft bulkhead, eliminating the need for cutouts in the interstage adapter.
Shortly after the 36A incident, NASA officials decided to shift the next scheduled launch, AC-6, to Complex 36B, which is adjacent to Complex 36A. At the time of AC-5, 36B was inactive. However, it was structurally complete. with most of the wiring and ground support equipment already installed. Some modifications were necessary to bring the facility up to an AC-6 configuration. For example, the horizontal swing boom assemblies originally developed by NASA for the Saturn program were installed at Complex 36B.
In tests at Convair, engineers evaluated the performance of the separation system and new latch hardware. The setup consisted of a Surveyor dummy mass model and a Centaur adapter assembly which houses the spring separation mechanism. An air-bearing, air-spring suspension system simulated, as nearly as possible, the weightless, friction-free environment of space. The spacecraft moved freely in 3 axes in response to separation forces. Instruments on the floating spacecraft detected movement and attitude change. The Surveyor dynamic model, which will fly on AC-6, approximates the operational spacecraft in moment of inertia, center of gravity location, and natural bending frequencies. The 2,100-pound model is inert except for telemetry and tracking equipment. No functional propulsion, attitude control, or other Surveyor mechanisms are installed. In April, Atlas 151D and Centaur 6C completed factory acceptance and moved into the interim combined systems test dock for composite systems checkout. In this facility, Atlas-Centaur 6 and the dynamic model were electrically mated. The combined space vehicle flew a simulated lunar mission to demonstrate overall systems compatibility. The composite test duplicated actual pre-launch and flight conditions as nearly as possible. After the demonstration, Atlas-Centaur was airlifted to ETR. In May, range crews erected AC-6 into the stand at 36B to begin pre-flight checkouts.
The countdown simulated an operational mission, with liftoff to occur within a limited time period, referred to as the window or launch opportunity. For AC-6, the target was not the moon itself, but a point in space 240,000 statute miles from the Earth. For the single-burn lunar mission, 3 points must all lie within the trajectory plane: the center of the Earth, the point of launch, and the position at which the moon will be when Surveyor reaches it. For Cape Kennedy, these conditions exist for only a few days of each month and for a time within each day, which may be only a few minutes or up to about an hour. 11 August 1965. Range is ready. Scheduled launch time, 9:31 a.m. or within 58 minutes thereafter, to begin a 63-hour Surveyor flight to the paper moon.
Centaur. Pressurization, go Atlas. Go Centaur. Hydraulics, go. Guidance, go. Spacecraft, go. Launch director, go. All recorders are fast, initiating engine start. Fast 10. Release. Full program in.
AC-6 lifted from the pad 4 seconds after 9:31. For 15 seconds, the vehicle rose vertically as the Atlas flight control rolled it to the proper flight alignment, which for this mission was 108 degrees from true north.
Program in on time. Secure out systems.
At about 900 feet, AC-6 began a programmed pitch maneuver that placed it into a shallow flight angle. It reached Mach 1 at about 1 minute into the flight.
We show a nice, smooth attitude control. This time, chamber pressures are good. Tank pressures are very good. Speed is good.
Aerodynamic forces increased with acceleration, reaching a maximum at 76 seconds.
Very, very smooth attitude control at this time. We show a nice set of chamber pressures and a very smooth transition through Mach 1 max Q.
The first stage of flight continued until Centaur's guidance system sensed an acceleration of 5.7 Gs. A signal to the Atlas programmer triggered booster engine cutoff and jettison.
Atlas, we have booster engine cutoff. Atlas, booster engine jettison. We show jettison.
8 seconds later, inertial guidance computed flight path error and sent correction commands to the Atlas flight control. At 171 seconds, the Atlas programmer initiated jettisoning of the insulation panels.
Centaur insulation panel jettison, all 4 panels. Panel jettison confirmed at AE.
25 seconds later, nose fairing jettison.
A nice smooth sustainer chamber pressure.
Centaur nose fairing jettison.
We have fairing jettison confirmed at AE.
Shortly after, the Atlas programmer starts Centaur's propellant pumps.
We show boost pump start. We have boost pump start.
At 234 seconds, it switches on the Centaur programmer, signals sustainer engine cutoff.
We have sustainer shutdown. We have SECO. Close vent valve.
Centaur vent valves close, tank pressures are raised to engine start levels, a shaped charge severs the adapter between Atlas and Centaur, and the Atlas retro rockets fire to widen the separation gap. For about 5 seconds, Centaur coasts. Then its main engines ignite, beginning the powered flight of the liquid hydrogen vehicle. The direct ascent flight of AC-6 called for an engine burn time of 432 seconds. Actual burn time was 436.5 seconds. Powered flight ended 11.5 minutes after launch. Centaur coasted 69 seconds. Then Surveyor separated to continue the 63-hour flight to the target. 5 seconds after separation, Centaur's inertial guidance system instructed Centaur's attitude rockets to turn the vehicle around in flight. 5 minutes later, engine valves opened and unused propellants began to gas out through the thrust chambers. The small reverse thrust continued for 16.5 minutes, enough to widen the gap between Centaur and Surveyor 5 hours later to a distance of about 1,000 statute miles. Surveyor maintains its orientation in space by reference to the star Canopus. If the Centaur were allowed to trail along behind the spacecraft, Surveyor's star seeker might inadvertently lock on to the reflecting body. Separation distance must be at least 209 miles. The paper moon target was based on the moon's actual position for September 28th. The simulated target would have been at this point, near the moon's equator. Surveyor SD-2, if no mid-course correction were used, would have landed at this point. It would have taken only a minor mid-course correction to hit the intended target. Since this was only an imaginary moon, Surveyor passed on through to go into the most highly eccentric orbit ever obtained, with an apogee of 441,765 nautical miles, a perigee of 90.5. The spent Centaur went into orbit 93.3 nautical miles out to 243,277. The two vehicles will remain in orbit indefinitely. With the first phase of Centaur research complete, development activities focused on the second phase, refinement of the two-burn Centaur. AC-8 is the vehicle which will continue the development initiated with AC-4, which flew in December 1964. It will go into an orbit 90 nautical miles high before engine cutoff. It will then coast for 24 minutes, after which the Centaur main engines will restart to thrust a dynamic Surveyor-Model into a simulated lunar transfer trajectory. Length of the second burn will be based upon velocity required rather than on a fixed time, as in the flight of AC-4. AC-8 is extensively instrumented. One of the measurements to be taken in flight will be tank skin temperatures during the full duration of the mission. These tiny transducers convert temperatures to electric impulses which are transmitted to ground stations via telemetry. There are 4 rows of them located 90 degrees apart around the tank. One of the major changes to AC-8 is the addition of a balanced thrust vent system. It is located at the forward bulkhead of the liquid hydrogen tank. 2 vent valves release gaseous hydrogen overpressures into a torus ring, which distributes this venting gas evenly to vent ports. The object is to ensure that even a small amount of thrust on one side of the vehicle is balanced by the thrust flowing through the opposite port, thus preventing spin-up of the vehicle during the coast phases. At the Eastern Test Range, preparation for flight began with the mating of Atlas to its launch pad, Complex 36B. After preliminary checkout, the Convair crew secured the adapter section, then hoisted NASA's high-energy Centaur stage into position. The spacecraft for AC-8 was a mass model made to duplicate the weight distribution and center of gravity of Surveyor. This is the final building block of the total space vehicle. In preparation for the mission, engineers exercise all systems, then put the vehicle through a simulated countdown, launch, and dummy flight. April 1966. AC-8 lifted from the pad 2 minutes after 8 p.m. Eastern Standard Time. It turned from its launch pad heading of 115 degrees to a flight heading of 103 degrees, then began a gradual pitch over into its shallow flight angle. The vehicle reached Mach 1 58.5 seconds into the flight, encountered maximum aerodynamic pressures 18 seconds later. The most efficient use of energy for this flight called for booster cutoff and jettison at the point where the vehicle reaches an acceleration of 5.7 Gs. This occurred at 142.36 seconds, close to nominal, 36 miles high, and 45 miles downrange. "34 seconds later, insulation panels jettisoned. A few seconds later, the nose fairing jettisoned. During booster flight, the Atlas sustainer was burning a fuel-rich mixture, resulting in depletion and cutoff 7 seconds early. Cause of the fuel-rich burn is not determined. However, the guidance system computed the error and later compensated for it by commanding an additional 8.5 seconds of engine time during the Centaur first burn. First burn placed Centaur into a 90 nautical mile orbit. This was the most significant period of the test, during which an important objective was successfully achieved, providing for the first time a method of controlling the behavior of the high-energy propellants over a full 25 minutes of zero-gravity coast. From telemetry data, Convair's computer produced this visual display of propellant utilization. The dots represent sensors in the tank. These disappear as the liquid level drops during the first burn. Real time is compressed into a few seconds. The data provided valuable information on propellant behavior during coast phase. After first burn, propellants were quickly settled and maintained proper position, as calm as a mill pond throughout coast phase. However, the supply of hydrogen peroxide was depleted, possibly due to a leak in the system. At start of the second burn, the propellant boost pumps, powered by this fuel, started but immediately began to slow down, presumably from lack of hydrogen peroxide. The main engines fired but decayed in thrust because of propellant starvation due to loss of pumping power. Centaur released its payload 37.5 minutes after launch, but short of the required mission velocity. The two objects went into orbit ranging between 96 and 188 nautical miles.